Hey everyone, Wojtek here, and today I will be starting a video or series of videos. I am not yet sure about optimizing the Godot for mobile, and this will cover things that can be done in the Godot, can be done in the assets, can be done on the Godot source code, and we'll dive deep. We'll do a deep dive into optimization. So I would expect you to be at least familiar with Godot itself, and the more advanced topics will require you to be able to compile the Godot. And I don't think this is a good video to start your journey with Godot, especially for like mobile systems. But if you want to optimize your game and you yeah feeling quite familiar with all the tooling that is available, then I believe this is a great place to start. And I really wished before that I had some kind of video like that for myself when I was starting. And quick disclaimer that we will go deep down into Godot shaders. We will use mobile profilers, tracers, real-time monitors, and we probably will deep down into the shaders assembly, and we try to optimize Godot shaders themselves. And so this is definitely more on the advanced side of things. And yes, but like first part of video should be for everyone, and I think that's where we start. So basically the basic settings in the default Godot that you can change, and how to look for things to improve. So as you can see, I have the game running, and this game is a mobile game with mostly static screens. And you can see right now I have around 45 FPS, which is not great for the GPU that I'm currently using, which is this Power VR B series BXM 8256. And I choose this device and this GPU specifically, and I really recommend to getting one of these Power VR devices because they are known to be crashing on default settings in Godot. So yeah, just for testing, try to grabbing one of those or similar. Yeah, so that's it. Let's start. Okay, so first thing I want to discuss is the renderer. So I'm using the OpenGL compatibility renderer, not the Vulkan Mobile or even Metal or anything. And it's because it's basically the most performant compatible renderer in the Godot currently, and this is what matters for me, at least on the mobile devices. And because I am targeting like a mid to high end devices, maybe I could try use Vulkan, but I decided that well, it would be best to get as many people as possible to run my game in a decent FPS. And still we have like 45 FPS on this Power VR GPU, which is really a middle class one, which is not great, at least to say. And it's even worse on other renderers. And another very important settings that you need to probably enable if you want to work with a mobile devices is vertex shading. So this one is saving a lot of performance as well. So the performance would be abysmal with this kind of scene and without it. But there is also another thing. Standard Godot shader will crash on this Power VR GPU otherwise. So it seems like there is some kind of bug in the shader itself, and it will basically not run at all. So if you want to avoid crashes or devices that are not compatible with Godot or any other kind of issues, I highly recommend forcing the vertex shading and working with vertex shading. It's good for performance on mobile, and yeah, basically it resolves a lot of other issues. And of course, visual, it's not the same quality as the fragment shader, vertex shading. I mean fragment shading, but yeah, this is obviously for a reason. And there are other settings that you may need to like tweak, like in the environment, for example. You can lower some things, but like I am not using a lot here. Anti-aliasing, I have everything disabled, but we can enable MSAA or other things later on, we'll see. But like for this profiling stage, it will be making things harder, so not really worth it. I would not using the light mapping, and it may be a good idea to use a light mapping in your mobile game, but because of the type that that I am making, it's not making a lot of sense here, so I am not doing that. And yes, I think that's mostly it. I think the rest of the settings are mostly set to default right now. So it's not really, yeah, it's not really worth like showing anything more here. Maybe I change some limits later, but yeah, for the performance reasons, this is not really that important. Yeah, so this is like a tour of the basic Godot settings that I currently have, and let's take a look at RenderDoc now, so to see where we can actually squeeze some more performance. So RenderDoc will give us overall idea how the rendering pipeline drawcalls are looking in our application. So first of all, if you already have a device connected to Godot, it should be showing somewhere here. So I have it already here, and I can try to connect it. And well, first time it will ask you to install some stuff on your Android device. You need to do that to make it work, and then it should have like this like replay context. Yeah, it's basically connected to your device. And after that, you click those three dots and select your application from your mobile device. I already have it here, so I would just click load last settings, and that should be fine. And let's click launch. So yes, and the game is launching on my device currently. It's not shown anywhere here, but I'm waiting for it to fully load and see the frame that I actually want to profile and see what is happening. So the device already loaded the app, and I can capture the frame, and you will see how it looks. Yes, so yeah, let's do this. Let's load the captured frame, and we'll see what Godot is actually doing. Yes, so this is how RenderDoc is looking for our mobile device. And yeah, so this is like a frame timeline and like preview of your current state of the textures, inputs, and other things. But currently, what we are mostly interested in, like, is getting to know what calls Godot is doing and what are those calls. So we can take a look at things here on this like left side on in the event browser, and we can basically click through the things that are here, and we can see what kind of like work the GPU is currently doing in this rendering pass. So first thing that we see is this GL draw elements instance, and as a matter of fact, I know this is the background canvas that is used as the sky, or yeah, basically the environment background. And this is of course this is rendering first thing, and you can see this is like the input. This is like a color texture that I'm passing. You can see the texture size, the MIPS, and in the output, this is like, yeah, basically the output is the full resolution of our device, and like the texture formats and things like that. And this one is actually interesting. Not sure what it is. Probably depth, but I'm not sure if we really need it here. But though, yeah, this is something that we can think about later. Like, yes, and we have depth only pass, which suggests us this is a shadow pass. So like we can see here that there is no inputs, but we have two output textures, which FBO is unused, and we have the depth texture. And of course, like if you go through the things, we can see that this is, yeah, indeed the shadow map texture. And yeah, we can take a look at the last call to get the idea how the shadow map is looking. So already first thing I can tell, this is using PSSM2, which I overlooked in the Godot editor, and this is probably not the best for the performance. On the mobile, I would use orthographic shadows, especially for like targeting low to mid-range devices. So I'm gonna switch this one. Mm, Also, you can see there is a lot of drawcalls, and I bet that some of those drawcalls can be optimized. But yeah, let's go to the next section, which is color path. So first of all, we have a background, we have a shadow map, and here we would expect to our scene to be actually rendered. Like we are in the depth, but we are not rendering to depth actually, rendering to this texture frame buffer, because like I saw that there are things that are added here, and of course we can see things showing up here like frame by frame, or like draw call by draw call, I should say. And we can take a note what things are actually like repeating a lot, or like what things that could be optimized, maybe grab. OpenGL in general doesn't like a lot of draw calls, but it will depend where's the bottleneck. And like definitely 400 or how many draw calls we currently have is too many, but we'll think about optimizing it in a moment. Yes. So we see that we draw a lot of like small elements here, and yeah, basically this is drawing all the elements one by one to our screen. So this is like a second section, which is the color pass. Yeah, and this is like, yeah, we can do some tooling here for better viewing. Like we can, I think not this one. I think this one is gamma correction and things like that. So this pass is basically probably the thing that we're gonna optimize for, or try to optimize for, because yeah, there is the most work that is being done actually. And what's next? So we kind of see that there's like draw calls that are after the color pass, and those are kind of interesting. So you can already tell, or maybe not, but this is the glow post processing. I can tell by the way it works. It's going from the resolution from up to down, and then we have the upscaling process, and yeah, we basically going back to the full screen, or maybe not yet, but basically this is the post processing pass where we do glow. So this is something we can think about optimizing. We may not want glow, but for this particular project I want it, so I will try to optimize it. And the last pass is UI. So this is probably easy to spot. Like this part here was the object rendering. Notice that it's darker because like every post processing, tone mapping, color correction, and I believe even the sRGB to linear conversion or linear to sRGB and stuff like that is happening in those passes. Somewhere here, or maybe here. Yeah, this is this is the post processing. This is the glow only, and after that we are using draw instance elements to draw the UI, which I probably not focused much on optimizing, but we'll see. And there's this last draw call, which is kind of interesting. and I believe this is just a bleeding to the screen basically. So Godot, because of how things are working and how it's composing the UI over the rendered 3D scene and scaling and things, doesn't render directly to screen. It renders to like internal frame buffer, and that internal frame buffer needs to be copied to the screen. And I believe this is this last draw call, which I gonna probably yeah inspect a bit more, or we gonna learn a bit more about this one. But like um, in this section, we kind of get the understanding what is happening where. So we kind of know the order of things, and this is gonna help us a lot in the next steps. So just let's confirm in Godot how does things are looking, and indeed we are rendering 400 draw calls, which is a lot for a mobile. I would expect it to be like around 100 something to be optimized. And the scene is going a bit more complex, so yeah, we may try to optimize a bit more. And indeed, we had where this we had the directional split set to 2, so we're gonna switch to the orthogonal. And also we could faster or make it faster a bit by disabling some objects being drawn to the shadow maps. So I'll try to do this. And like I noticed that some objects are actually a lot more complex than they should be, like this mesh. For example, I yes, open anyway. Like you can see it's combined like multiple parts, each is causing multiple draw calls on OpenGL render, which is not great because it seems like it's not batching it in OpenGL automatically like it does in the Vulkan. So I will do those optimization and we will see how things improved. Quick thing, because I forgot to mention, is that we will also take a look at the video RAM tab. So when your app is running on the mobile device, which is doing right now, you can see this tab here, which is video RAM section, and just click this reload, and you can scroll around and see what kind of textures they have. But most importantly, is what kind of format they are using and what kind of size they are. Probably will try to shrink everything as much as possible for this title because everything is quite small on the screen usually, and I don't need 2K textures and things like that. So I'll do this as well, and I will show you the results later. Okay, and after those changes, you can see the current stats here. So the FPS really didn't change that much. It went a bit, of course, but I would expect a bit more over those changes. So what I did is like I reduced shadows casting from like some items and like I merged some geometries. So we reduced the draw calls quite a bit. Actually, it's 161, and but well yeah the output and FPS is still not the best. So we will go further and we will try to investigate what is actually causing the issues. And for that, we will use the other tooling that is for specific vendors. So in this case, I will use the PowerVR um, tools, but you can use similar stuff for Mali GPUs or Ardena GPUs, which maybe I'll show later. Yeah. Okay, so we are in the PVR Tune Developer, and basically, if you have already connected devices to Godot, it should be showing here. You may need to turn on debugging and off and some stuff like that. And I will not choose the application here, but you can, because it's already running on this device, but you can choose it for sure here. And yeah, we'll see what is happening. And this is quite interesting view for multiple reasons, but the most interesting things are probably here somewhere, which shows you a bit more details what is actually happening. So this is like in real time view, but what you can do is like you can zoom in with control scroll and just scroll a bit to see actual things on screen. And it may look a bit cryptic right now, but it's actually quite simple. So what we currently seeing are frames that are being rendered on our mobile device, and we probably will be interested mostly in this hardware render section and hardware geometry. So to put things simple, the geometry is related to the vertex shaders, and this render section is related to the fragment shader. Mostly, this is tile-based render, so it's a bit different than like standard rendering on the PCs, but yeah, we can like simplify this, at least to my understanding, things like this. And you can see there is like some already like a graph over those like other frames details, which I enabled before, so we can disable it for now. But this is quite interesting thing that we're gonna look later on. So first, let's try to understand what we see, and there are a few interesting information which is in this like red top color above. This is the PID ID, which represents the process, and usually you can see other PIDs here as well. And what it will mean is that there is other software that is actually using the GPU, which may interference with your application. So that's thing that you should eliminate. And this is 24150, which is our application, because I don't see anything else actually. So we can actually see here as well that this speed is using the GPU quite intensively. So this is it. And other thing that we can see here is this like the big section here, and I think this big section here is actually representing the frame. So this is like saying you this is the frame number 65,046, and this is the frame 47. Yeah, so this is the frame number. So this is basically telling you this is the single frame that we saw in the RenderDoc, and all those like tasks here are related to this frame. So if you hover over it, you can see that this frame took 27 milliseconds. 20, yeah, in the top on the screen, 20 almost 28 milliseconds for this frame, which obviously is not great. We are targeting at least 16 milliseconds, 16, so to get 60 FPS. Yes, so we know this is the single frame, so let's take a look at this single frame. And the section below is actually, I believe, representing the current render target. I may be wrong on this one, it's not really showing it that great, but it may be. So this is like showing you what kind of render target we are targeting currently towards. And this is useful to recognize the shaders basically. So we will know what kind of shader it is because we are running different shader on different render targets in Godot, and we're gonna investigate a bit more. And from what I understand currently, looking at this and looking at the previous RenderDoc graph, like this thing. Okay, so we actually disconnected the RenderDoc, but we can still take a look what we had. And yes, we can kinda start matching stuff here and there to get the understanding of what is rendered where. Yes, so we can assume that this stuff here is probably our main pass, and because this is like the biggest, render pass to the single frame buffer, and those smaller things here and growing things here are glow. This is from also this observation that those passes are rendering to the smaller frame buffers or render targets, and they are growing again. So it kind of matches the glow pass. And somewhere after there is UI and copying to the screen and stuff like that. But this is hard to tell from this view what is actually happening and what we are interested in. So let's actually take a look at those things on the left, and we can draw a lot of things like FPS, which is not really that is interesting in this case. But we can take a look at two things that probably will decide what we gonna do next, which is the geometry active. And you can see that we have a geometry active in some places, but not in a lot of places. Like during this process, we have zero, mostly zero. And you can see that this is like 9% overall. So that would mean that this is actually not that intensive. So geometry is, as I said before, related to the vertex shading, and we have renderer active, which is related to the fragment shader mostly. And this is 10% thing. There is no like in between, but we can clearly see that 99% of the time we are like very active on the renderer side. So we can we can also enable like other interesting things here, like processing pixel load. So we can see that like we are very hard on the pixel side compared to the processing vertex side, which is almost non-existent. So what does it mean? It means that our fragment shader is probably very expensive on those runs, and that's the place that we probably should focus in on. And it's also interesting to see that our processing load on the pixel side is the most intensive in this area, which would probably represent our standard draw, so our color pass. And that also help us deciding where we should focus after that. And another very interesting statistics we could take a look is register overload. Like on the pixel side, we can see that we are almost hitting 100% of the register overload, and we can read a bit more in this, like a properties tab, which helps us to understand this. But what it means basically is that our shaders are too expensive on the register side of things, so they are using too many registers, and well, we cannot run uh, such many concurrent instances of the same shader, which obviously makes things slower. And yeah, and we can see that in the glow pass it's also quite expensive. I think there's like the copy and UI somewhere here, but it's kind of hard to tell with this graph alone. But we're gonna use other tools with other GPU vendors that may give us a bit more insight of to what is happening. But yeah, overall, like we can clearly see that the fragment shader is kind of the problem. And yeah, we can take a look at other things that are here that may help us, but I think that this is obvious currently what we should focus on. We can also take like GPU memory interface load, like read bytes and like write bytes, and like let's disable the other one to not get like. We can see that this is also quite high in some places. That's actually this view. So it's like we are really hard on the memory, and it's even hard to tell what is visually happening because it's basically over the scale. But yeah, we can try to pinpoint some places where this is expensive. And we can see that there's some vertex shader work here, but compared to the fragment shader, it's not that much. So what we can do now is we can go to the RenderDoc, we can capture some of those fragment shaders that are running currently for every object in our scene, and we can investigate it further. So we're gonna continue with that. Okay, so here we are again in the RenderDoc, and we are actually on a new, fresh, new capture from the our application that was a bit optimized, and you can see we have a lot less like the drawcalls and stuff, which is obvious because we saw it already in Godot. But yeah, we now know what to look for because we check this in the PVR Tune, which is some things related to the color pass. And we can take a look and look for like a very big objects and things like that. But as we already noticed that our vertex shader load wasn't really the biggest, so that was not the issue really. So not really something we were gonna look for. And I'm gonna select this one because I know what it is. So you can also basically take a look between like before and after and see which object it is. And this is like this bush one here. Like maybe we go with the third one or fourth one. Okay, I think there's a double one, but like basically we select one of the bushes, and what we wanna see right now is the complexity or how expensive this shader is on our mobile GPU. So how to do this? So we select this draw elements or draw call, any kind of draw call, and we kind of confirm what it is. We can go to the pipeline state. We can also confirm, like looking here, what kind of texture it gets. So we are more or less aware of where it's, what is rendering. Like we go to the pipeline state and we have like multiple things here which can be interesting to us, like vertex shader and like uniforms to the vertex shader, and like we can click this go to basically see a scene data block, and like see what kind of projection matrices and things like that. But this is not really what we are after right now. We are actually after the frame shader, fragment shader. So this one, and we can see all the things that we are using here and like things that I don't like already. And yes, so we could probably simplify a lot the basic Godot shader. Like we can see there's albedo, metallic, and roughness. We don't really need a metallic and roughness in this simple scene on a mobile. That would save us a lot. And if we remove that one, maybe it will improve the performance. But yeah, that's something to take a note for, and we're gonna investigate it later on. And we can see that they are 4x4 texture, so they are doing nothing, and this albedo texture is quite optimized already. You can see that shadows are 2028, 2K by 2K. Yeah, so they could be smaller because this 16 is kind of not compressed format. But yeah, anyway, what we want in the RenderDoc is actually the shader, and there are two things we can view and we can edit, and we're gonna click edit because it's a cool feature that will allow us to actually confirm that everything is correct. So right now we get this like fragment shader, and we're gonna do this from RenderDoc, not from like sources, because well, Godot compiles the shaders, and we are kind of interested in this particular version of the shader because this is the shader that is actually expensive on the fragment shader that we saw before in the PVR. So what I'm gonna do is I'm gonna copy it, and I'm gonna go to the Visual Studio, and I will create a new file here, and I will save it in the PVR profilers folder, and I will call it like fragment tutorial. Let's see, and it will be frag because it's a fragment shader. And this is one thing I noticed that Visual Studio doesn't color it correctly. I will use C++, and it will be mostly fine. And we got this shader, which is goodish, I would say. It's still not great for debugging. There's a lot of those if defs that are making it investigate very, very, very hard. So what I thought about was actually using the GCC preprocessor to pre-compute all those things, and we should get the same result, the code result, but without any of the preprocessor stuff, which saves us a lot of hassle. So let's go with this one, and we were gonna use this command, which well, you can probably run it on the Windows side, but I'm using the Whistle, which is basically a Linux machine in Windows. So I will input a fragment shader tutorial, and I will call it maybe pre-processed fragment tutorial frag, and press enter. It will give you a lot of errors because I made a mistake, because we want to actually pipe it down there. So now this command should be good. We got like a lot of warnings and stuff, but we're gonna look for this, and yeah, there's a comment above we can remove. We can again use C++, and we can see that we went down quite a lot in the code. So currently we have like 600 lines of code, and we were in 2000 something. So this saves you a lot, and there's a lot of like function definition, like this user's definition, which also does nothing. So you are only left with this fragment shader One thing that we are missing and we need to copy because the preprocessor of C++ doesn't really know is that we need to have this version here. Because it's saying us this is a version 3.0 OpenGLS, which is important. But yeah, we get the full shader for the standard color pass of single object in our Godot pass, Godot application. And what we can do with that right now is like you could analyze it by looking at it and saying, oh, okay, this is something wrong here, or I don't like how complex those instructions are, or maybe you are doing something in the wrong order. But this is not very efficient way of optimizing it. And some may say that, well, optimizing for like single vendor is not great, but in my opinion, it's better to get like overall idea than like going blindly. So what I am using in this video, I'm gonna use this profiling compilers for the PowerVR again, but I believe there's something similar for Mali and other like Arduino. And you download this will gonna be a zip, and yeah, it's gonna basically you're gonna extract it somewhere, and I have it here, and I need to be on the Windows side, and I have this profiling compiler 3 wrapper, and you can see this is help. So this gives you a bit of understanding how to use it. So for example, to see how expensive our shader is, we can do an API of course, our API is OpenGL, and B, it's basically the hardware that we are optimizing for. And I like to actually use this one, which is exactly my GPU, because the assembler that it outputs, and we're gonna think about it later, and it's kind of nice to read and understand. And what next? Next, we're gonna use type. So we're gonna use the fragment shader. So TF for fragment. And we're gonna use the input file, which is preprocessed. No, we're gonna use preprocessed fragment tutorial frag. And it's gonna output a lot of things that are scary, but what is most important is gonna create another file, which we saw here, .json, which is named the same as the input file, but with JSON extension. And we're gonna click this one, and this is our input shader, and this is our JSON file that it generated. And it gives you a lot of useful information that you can learn about, like utilization, estimate, clashes, like number of reads, and total number of like registers. I believe there is somewhere total number of temporary registers. Yeah, this one is important. This is very bad value. And the number of instances the shader kernel can be run in parallel. This is also the thing that we want to maximize. And like a knife cycle count, it's a knife cycle count, but yeah, basically probably gives you the worst case scenario. This is also something you want to optimize. And by looking at those things, you can kind of get understanding what part of the shader is actually causing the issue. And yes, so you can number of sample operation. We can see that we sampled 6 textures, and we have total number of cycles in the post feedback phase and pre-feedback phase. So my understanding goes those two is actually number of cycles that are executed before sampling and after sampling textures, or like any heavy memory stuff. This is like vendor dependent things that maybe not the most important one to focus on. So this is like JSON version of those numbers, but like for comparing things, I actually like to execute it with the -x, which outputs you the stuff to the different folders, different files. So -x will generate two different files. You can see assembler and prof. So prof is basically the same number that we had in our JSON here, but in the more compressed version. And assembler, well, it's assembler, but in the readable format, so we can basically read stuff and see. And one thing that is probably the most interesting is in the profile. We can see utilization, which is 57%, and max parallel instances, which is this one. And this is telling us basically that our shader is not greatly utilizing our resources, and we could squeeze a lot more of parallel instances if we gonna optimize some things. And we just have to take a look at the shader and see what we can cut, move, replace, or what kind of instructions. So probably the first very easy thing to do is trying to basically reduce the naive cycle count, and maybe we try to minimize the temp register count somehow. And so I will try to do some modification and describe what I did to and how I came with the ideas. Okay, so in the preprocess fragment tutorial file, let's start with the simple stuff and let's try to optimize the Godot shader. So you can see this shader, this part of the shader is actually something that we generate in our 3D shader files or whatever we call them. And we notice that we are using metallic and roughness textures, which probably are not needed. So we can do this in the Godot side, but because we would have to read this full shader and do all the stuff again, we're gonna do this here. So what we're gonna do is, well, we're gonna remove the unneeded things. And this texture sample dot is definitely unneeded. Specular roughness texture, this is also not really something we need. And this is something that we should end up with, I believe. And we can remove the sampler. So let's see where it is. Metallic roughness, and this should improve the things. Sorry, I have this one here prepared for tutorial, and this is the old results that we had before. And what I like to do is I like to copy this one in the new file. I like to press, I call it original one. And basically what I do is I select it in the Open Editor tab, like this. I select it for compare, and I select the generated file and compare with selected. So now I know that this original shader had those values, and whatever we do to our shader will be on the right side, and we're gonna see direct comparison. So I did those changes, and only thing to do is basically run this again, and we'll see. So right from the bat we can see that we improved things a lot in some aspects. In some aspects we didn't, but it is what it is. And we see that we went with the naive cycle count down to 500, which is not to 550, which is of course not a lot because we just removed some samplers, and we reduced the instruction count. But what is more important is that we increased the max parallel instances to 4,000, 4K from 3.5K, which is great, and we reduce the temporary register count, which is basically impacting the parallel instances. The lower we get with temporary registers, the higher the parallel instances probably go. And we see also the utilization went to 66% from 57, which is great. So everything we did is only removed some simple shader changes, and it gave us a lot of performance improvements. But this is the simple stuff that we could do, and the stuff that I'm most interested currently in reducing is the temporary register count and knife cell count. So at this stage, you may consider removing some stuff that your particular project is not really needing. And if you think about it, this shader that is going to be generated uh, will gonna have the stuff, the instructions, and the count and the things like register usages, even for the conditional that are probably not used. Probably some new architectures can work around it, but like for ease of debugging, we're gonna basically try to remove as much as possible, and and see how does it impact the result. So what I think I can use or remove is the specular part of the um, uh, environment texture. So because we are mostly in the like rough albedo stylized rendering in this game, I think I can remove some texture samples for the specular light. So I'm mostly interested in this part here, that is actually introducing some stuff to the reflection specular light using texture, which will remove one texture sample. Will remove the sRGB to linear call, which is a good thing. And we're gonna see how does it impact. So we can remove it. And one nice thing about RenderDoc, I'm gonna show it in a moment, but if I remove it, I'm gonna try to compile it, and I'm gonna see how this is impacted. So right out the bat, we can see that our cycle count went down a lot. Our temporary registers are now 21. They were 24 before, if I remember correctly, and our utilization went up to 72%. And but the important question is, we removed all this thing. So how does it impact the visuals? So we can copy this shader actually. We can go to the RenderDoc and we set the, we click the edit. So we can remove this shader here. We can, click and apply changes. And the texture viewer, it should be visible. So it is probably visible, but the difference is almost non-existent. So that's a good thing, because all of our things are not really heavy in the shader and department. I mean the specular light department. So this is helping us a lot. And if you want to be sure that our fragment shader is really updated, we can like multiply it by 0. We can apply changes and it should be black. And you can see this is working. So we kind of saved a lot of um, you know registers and cycles just doing those simple edits to the shader. Of course, we need to move them later on to the Godot itself, but like for optimizing, this is the great part where we can see the result. And like we can see that how the stuff improves and test it very fast here. And yeah, so we're gonna do more than that, of course, more than that. So we have a lot of instructions and life cycle counts, and I believe there is some heavy computational things that we could simplify. So for example, linear to sRGB and sRGB to linear. This is, of course, a more correct approximation, but there are other, and let me find it. Yeah, so I have it here. So now we can see that this one is a lot faster because POW method is very expensive on mobile devices, especially on devices like PowerVR or Arduino or lower class GPUs overall. So by doing those modifications, we have those numbers. So just not to forget what was our previous number, we can basically copy this current version that was before this optimization and copy it here to see if this further changes. Yeah, or we can, do totally different file. Well, yeah, doesn't really matter what we're gonna do, but important thing is that we want to see progress every time. So like I copied it back. I know that this is a lot better than what was originally, but it still could be better. Yeah. So let's see how well does that. Let's save this file and let's go back to here and let's try again. So we have a success. So just to be clear, this sRGB to linear was fine, but this linear to sRGB was expensive, and it was used, well, 2 times and maybe even 3 times, if I remember correctly, for the radiance map before that we removed. So you can see just by switching this instruction that is not using PWO, we went down in the life cycle count almost by half, which is crazy if you think about it, like how expensive this method is. And our utilization went up to 79%. And our temp register count is actually at 19 currently, which is quite good. Is it quite good? Probably it could be better, but yeah, let's think about it later. So yeah, so now this is interesting because we can see that we changed the sRGB and linear to sRGB, so we're probably gonna see some difference in the shading. Not a lot, but I expect to see a difference. So again, we can go here, can apply, and it's very hard to tell. Let me actually move it here. So yeah, we can see that our fragment shader, yeah, this is with the changes applied, and this is the original shader. So it is a bit more mild. The sRGB to linear is changing it slightly bit, but the performance impact is enormous, and I think it is definitely worth it. This is not, of course, physically correct, but it is fast, and that's what we want on the mobile device. Yeah. So now the simple things are done. Let's think what we can do more here. Okay, so now a bit more advanced topic that I want to speak about is sometimes those numbers that you see here are, yeah, very interesting, and you can kind of rely on them, but usually what it means is like whenever you got those numbers, you have to check them in real environment, and basically you need to modify the real Godot shader back, and it is of course kind of complex. So we're gonna discuss about it a bit more, especially with those e-defs that we did. I mean, these current optimizations are quite simple, so they shouldn't be that bad to port, but yeah, it might be something that worth showing. And one more thing that is probably not showing a lot here is something called textual restore. So sadly, we don't have the view in the Power VR toolset. So for this things, we're gonna go with the kinda assembler way intuition. So what is a texture stall read is usually a texture load that is missing some caches and stuff. Basically, any texture read that is happening, and GPU needs to wait for the result of it. So I don't know if there's a better way of this, because like for my device, it's gonna but like the texture tab, it doesn't really work in my device. I guess it's like the limitation of the driver. So what I like to do is I like to take a look at this other example. So I have this prof file, which is basically the raw numbers, and the assembler file. And this is why I said that I like the output of this how it's called, BXM, and yeah, this driver version, because it's giving you this like very nice descriptive assembler, which may look a bit complex, but in the end it gives you a very good description what it does and where it does it. So you can kind of see things like coefficient register mapping, which is basically varyings. Those are like blocks data that come from uniforms and like, yeah, basically stuff like that from the CPU. And there are other interesting things, and like this register mapping, relative offset addresses, and this is like a main program. And yes, what we are actually currently interested in is checking the sampler types. So first of all, we can take a look by searching type SMP in this assembler, and we can see that there are three texture grids. And what is a texture style is a type of type assembly command, which is setting the same kind of register. This is like a textual sampler register, and waiting for it. So we can see clearly that this first instruction in our shader is actually trying to read the image, and it's waiting for it. So it's blocking grid. What we want to do is actually have a sampler instructions, some arithmetic operations, and then we want to have read from. So the wait for this DFC data is delayed. So this basically means that we are reading the texture, and the next instruction is probably just using the data from this register, um, or something like that. And you can dive deep down, and like you can see, destination register is R13. Okay, I clicked wrong, but it is R13, and well, this here. So I expect R13 to be used somewhere near here, but yeah, this is blocking. So we can take a look and see like state-based image. We can search for this H14, and we can see that there's something above there. And this is for 400. And SH14, it seems to be M-texture albedo. So this is albedo material from our texture shader. And we know this is kind of hard to avoid. So this texture stall is gonna happen because, because, well, we cannot really modify the position in the full shader albedo rate. And in our Godot shader, these two are basically one after another, and we cannot do a lot with that. But like, let's see if there's more, because this is like user-defined shader. But we have next one, which is this one, and this is also waiting for DFC1, and it's setting DFC1. So this is not good. This is bad, and let's see what kind of image it is. SH10. Let's go to the top. And this is the radiance map. This is a radiance map. What does it mean? It means that this is our PVR workflow reading this radiance map and instantly trying to use it. And let's see actually where the radiance map image is used. We can go back to our fragment and let's search for the radiance map. And we can see 3 instances. This one is no longer here. I mean, this is the fog. This is the light map override thing. Okay, this is the ambient light actually. So this is the only one, because the third one is the definition. And we can clearly see what is happening here. So we are reading the texture radiance map, and we are doing the sRGB to linear right after we read it. And this is in the if block. And this is not good, because the compiler doesn't know if it can optimize this call. So the problem here is that the send data block is happening here. So the shader compiler cannot move this call somewhere up in the call stack. So it's basically not waiting for the result of it, and it's doing the other arithmetic operation during the loading of this texture. But we can probably do this ourselves. So let's think what it actually needs. So this cube map textural D will require the radiance map, which is well uniform, and ambient dir, which is this thing, and this thing needs a normal and some sane data block. So I don't like it here. Let's say I can comment like stuff moved from here, and let's see. I will assume that in my game I'll always use the ambient cube map in all the scenes that I have, so I can safely move it. And where I want to move it. So I think I need to normalize the normal, which is kind of important because we have normal interpolated, and this will result in non-normalized version of it. But in general, I think I can move it somewhere here, and this should be fine, except I need to add a normalized call. But this normalized code should be quite cheap compared to the stall on the texture, so I will do this like that. And we move the cube map ambient, and we left other stuff in the in this block. So this is not great. So because we assume we always use that, we can remove this if, and we simplify the conditioning. So now we're gonna use the cube map only when it's needed, but we're gonna sample it in the start of our shader. So there is no stall and there is no wait for it. And that should allow us to speed up our shader. Of course, this is assuming that, well, there is an alpha scissor call, I think, somewhere here. Or maybe there is none. I think there should be. Yeah, this is alpha scissor call here. So we are sampling the texture before alpha scissor call. But this is, well, still better if we assume that most of the pixels are opaque. So we don't kind of care. We still sample it everywhere. So this is like under assumption like that. But let's see how this is impacting our shader stats and our shader. Yeah. So we're gonna call this function again. I mean software. And what happened? So first of all, I don't think much really changed, and in the aspect of those stats, maybe something went down. We didn't do a copy before, so hard to tell. But like what I am interested in is looking in this fragment shader, and let's see, type sampler. So the first one is albedo. We know this is stalling. We can't do much about it. The second one, is still stalling. So what it means? It means that the operation we did wasn't really enough to remove the stall. Yeah, so we can think about it and like maybe we can move it further down the line. So let's see, I don't need this in the if conditional. Let's say this is always happening in my case, so I will not doing any kind of conditionals, and ambient light is gonna be somewhere below. Okay, so we did comment the if statement. Let's see if this change anything. This could allow the compiler to move stuff around, and maybe, just maybe, it can remove the weight. So this is the, and I think we actually did it. So just by removing the if condition, it seems like this is the first, which is albedo, and this is the second, which is the it was the radiance map, which we see that we have a set for the FC1, but we don't have a weight on the FC1 after this call directly. And like we have a weight here, which is how many? 1, 2, 3, 4 operations. So we kind of saved a bit, not so much. So maybe not worth it, but this is something that you need to profile in your application. and basically they go look at the FPS and like time frame is taking, and those things may matter on the lower end devices, and you can do a lot of more of optimizations. So one thing worth mentioning is, as I said before, we are optimizing for the specific GPU, and we kind of can see what else we have. So we are optimizing for this one, which is kind of high end, I would say. I mean, mid range GPU, but high end for the Power VR. And this one is like the worst case scenario. So if we're gonna go with this one, we're gonna see totally different numbers. So let's do that. And let's see, let's change this for this. And yes, so we have something. And one thing you notice that even though it generated the same file, it actually gives it a lot more like informations, you can say. And obvious thing is like utilization went really down because it's a really lower end device, and that's basically not great. And you still have some like things that you are aware, and there are other things you can read the new JSON it generates as well. There's a lot more, but like this is like floating point used, complex operations like temp register count. This is something that you really want to minimize, and this is hard. This is the hard one to get below this like magic value, because like choose the brush shader which I wrote. It's kind of easy, but like if you're gonna use the default Godot shader, it's gonna be a lot harder to optimize for it. So this is like the process that I'm doing usually to see this like optimizations, but there's more that we can think about. So let's see, we have this like this is the file, I believe, preprocessed fragment tutorial. Yeah, so we can move it to the left. It's here, and we can compare. So like we have utilization of 33% and like temp register count 25. Like one obvious thing I noticed is that we are using the varyings for the vertex shading, and those varyings are kind of expensive. If you take a look here, we have invec-free, diffuse interpolation, and peculiar light interpolation, addictive, and they are using default cons, the default precision, which is taking the precision from float, which is defined the top, which is high precision. So those variables are high precision variables, and this may be very expensive. So you could try to make them medium precision variables. So in medium P, in medium P, medium P, in medium P. Of course, you need to modify it same way, I believe, in the fragment, in the vertex shader. I mean, it would make sense not to use the full precision if we are not gonna use it. But let's try to see what kind of result we're gonna get. So probably not much has changed. This, I don't think a lot has been changed. And those are the things that you're gonna need to try. to optimize um, your vertex shaders. And these things gonna matter. Like, it may be that changing those values here didn't really result in the reduced uh, complexity, because the diffuse light, for example, is still vec free, and it may actually result in the, you know, increased complexity, because instead of optimizing the fragment shader, we're gonna make it more expensive, because now it needs to convert those things, and things like that. You basically need to take a look and take a look at the knife cycle count instructions or temp producer count. Oh, it went up. So what does it mean? It means that something is not right. Uh, and we kind of added a conversion somewhere. So you need to track down all the places where this gonna happen. And yeah, so let me pause here and basically try to optimize for the kind of best result that I can achieve right now for my use case. And this is like a version that I end up with. So first of all, I changed the overall precision to medium P on the float side, and I don't see any kind of like a downside. It may be quite risky, so you're doing it under your responsibility. Every change you do here is on your own responsibility. Simplify a lot of like stuff that we kinda don't use. So yeah, I removed the fog process because I don't really use fog. I added a comment why I moved it here. I changed the medium P precision to the beta, but to be honest, like I also removed the specular, like optimize the shader itself. And yeah, I removed the medium P because we kind of set it to default. I also removed some EBL calculations, like we don't use the specular stuff, so I removed the specular lightning code that was related to the global illumination, because well, we don't use it anymore, so why should we waste resources here? And like you can see, I optimized it quite a bit, and probably the most interesting thing is think how we progressed. And this is the result. So we went from the 110 to 88 day cycles. FCU utilization, we went to the 58%. And this is kind of good, I would say, compared to what we had before. We went really down with the register count, which is the most important, from 27 to 18. This is probably the stuff that made it, go into utilization, and like parallel instances went up a lot. So this is saving us a lot of time, and it may be kind of bad in other aspects. Like there's one more wait stall, but well, it's still better to run a lot more, probably a lot more shaders in the same time than like removing this weight. So in general, this is the current version of the fragment shader, and we can go and test this and see how the performance changed. And you should expect at least like 10 to 20% from what I saw. But we're gonna go further, and we're gonna focus on different things like post processing now. So we're gonna use the different device for this case, and we're gonna go with this Arduino Snapdragon Profiler, which gonna give us a bit different insight on what's happening inside the GPU, and we're gonna use the system trace analysis for this one, and yeah, we're gonna use our Godot application, which is um, our game, and we're gonna go with the OpenGL. We're gonna press launch, and here we're gonna select a few things that are probably interesting to us. So in the process, in the GPU general, we can take a look at the clocks. We can take a look at memory stats, preemptions, primitive processing, um, but I am mostly used in the shader processing and shader stalls, I think, since I know that the post-processing stack is actually taking a lot of time. Since I noticed it in the Power VR, I am like dropping like 30 FPS whenever I enable the glow or whatever. So we're gonna do like a shader allo capacity, shaders busy, texture pace, shader stalled, time allo working is also good, time shading fragment, and what else? Fragment shader shaded, and we're gonna use textures in the fragment. So basically will tell us how many texture samples we are doing per fragment, and we can see fragment allo instructions as well. The stalls. So texture fetch stall, vertex fetch stall, I guess. Miss, texture miss is also good. And per drawcalls and rendering storages are something that is worth monitoring. And I believe that's it. So we can change the duration, and I like to set it to 1.5 seconds. And this is not the real time duration. It's gonna be slowed down, so we're gonna take it a bit longer, and it's gonna take a time. So it's rendering stages now, and yeah, I will unpause when it's done. Alright, it's done. So the view is looking like that, and you can see there are multiple things that are probably interesting. And whenever you zoom in, you're gonna see a lot more. But basically, I can tell that this is more or less one draw call from here to here, and this kind of steps are repeating. So this is looking like a good like first call, and there is like a binning here, so you can see it's probably rendering to the screen here. And there's a lot more that you can investigate in this view, and but what I wanted to speak about is basically noticing some kind of issues. So first of all, even though those calls are not so big compared to so this one, it's still worth noting that it is not representing in real time. So those calls took a bit longer. So what we're gonna do is actually we're gonna take a look at the workload, not like specifically in time, but like per draw call. So we can do this by showing the draw calls, and obviously there are some problematic things. So we have like big draw call here. So this seems like an optimized shader of some kind. This is a very big one, and not sure yet what it is, but texture samples. So it seems like this is some kind of object that is actually very heavy on the fragment shader. This is worth investigating, or maybe two objects. And here as well. But I am mostly interested in the post-processing. And from what I can tell, we have one big issue. So this is glow, because glow is working towards smaller surface and going back. So it's very clearly easy to spot that this is a glow effect, because this rendering times are getting smaller, because like surfaces are probably also getting smaller. So you can check it, like this default light green is 204 the resolution, and it's full screen, surface width and height 2400, and this one should be half. Yeah, this is 1200, and this is 600, and going down like that. So we can tell that glow shader um, are very choked by texture fret stalls, and it is clear why, but we can also tell that what is worrying is that this first step is actually stalling us a lot, and I believe this one is still not full resolution. So this is actually last step of the post-processing. It's so freaking expensive. In the allo, in the texture pipes, um, time shading, fragment, everything is super expensive. Um, and we sample 12 times the texture. So by optimizing those two things, we can clearly see that even in the bigger picture, they're super expensive. Like there's something here that seems expensive, but it's actually a lot of small calls, and I believe this may be UI actually. But like this is the single call, so this is like something obviously wrong. Obviously too expensive. So what I suspect is like we are doing glow in the full resolution, and this is why what is causing it. Like we're trying to upscale and doing more texture samples than we should. So just by looking at those things, you can kind of get the idea what is wrong. And you can also try to measure them in other software, like in the Power VR. Yes. There's a lot of other interesting stats that could be helpful here. Like we don't see a lot of like going on, except this maybe drawcall, and this is the previous frame already. So yeah. So there's something big rendered a few times, but nothing crazy. A lot of like smaller drawcalls, and like one huge time waster, which is post-processing call. Yeah. So I do believe event browser. I do believe this is like the first one in the color bus. So this is this one. So this is the yeah, we probably don't have access anymore because I disconnected that device, but like we can see how many vertices are in this call. We didn't took this statistic here, but basically we can do another thing, which is snapshot, and we can search for this like behavior by looking at this draw. We can pinpoint it further. So like let's do that snapshot GPU frame capture, and let's do a capture quickly. And yeah, launch. Okay, that doesn't really matter. And we are interested like everything like in time, department, shader all, ML, shading fragment, and textures fragment, I believe. Then we're gonna try to pinpoint the draw call that was so expensive. Mm, okay, let's take a snapshot. And we have a snapshot, so let's search for the call that basically was super expensive. Maybe this one, maybe the next. Let's see by the texture samplers, there's gonna be this one, 12 texture samples, which is crazy. And yeah, so we can basically see what this shader is by investigating the fragment here. We can see the other statistics, but you can take a look. This is indeed the post processing shader. I recognize the calls here. So this is post GLSL. So this is basically a last step of the post processing, which is combining the glow. And this is the most expensive one we have so far. Yes. So basically, we're gonna do the same with this shader, and we optimize it using the same tooling we did before. And yeah, the PVR Pro, offline compiler will do the same. I mean, it's obviously a different architecture, but if you spot such an obvious issues, then yeah, then you're gonna fix it. Like 12 samples and like a lot of algo for full screen. It's definitely not great. And you can see that linear to SRB, we see again the POV function. So there's a lot to optimize, and we probably can choose better tone mapper, a lot of things again. But yeah, I will pause here and I will optimize offline. Okay, and taking a look again in the Power VR tune and just showing the same issue from a different perspective. So what we are interested in the Godot and overall post-processing stack, I recommend reading a bit source code to get a general idea of the Godot. How does it work? There's also this great like website with articles about like blurs, glow, and like how they implement it. And I believe that Godot has implementation of dual Kavase blur, which is probably the most popular one for the overall everywhere. So this is nothing really too crazy, but like you can see how does it affect like other things like parameters. You can tweak it. You can take a look at like WebGL implementation, a simplified version, and like the simplified shaders to get a general idea how does it work. So from what I understood so far, the dual Kavase filter that we are having in Godot is actually 4-step downscale and 4-step upscale. So we have like we can confirm because like we can select the first draw call, which we are now. This is um, a glow one because this is like a filter step. So um, we can extract again the fragment shader, edit, let's copy it, and let's go to the visual code. Let's copy it and let's, yeah, it's a C++. So Godot is using something called like modes of the shader, and you can see we have three actually: mode filter, mode downsample, and mode upsample. So it is a bit different from what you're gonna read because we have like a mode filter, but mode filter is basically doing the same downsample step and some filtering. Like this is the additional math. So yeah, that's it. And this here, this drawcall here is the mode filter, which is first one, which accept those additional parameters. And like we can have texture viewer here again, so you can see, and we have one. I mean, this is the first step. This is the second step. This is the third step, and this is the fourth step. And this is the smallest one. So the fourth one is the smallest one. And we have again one up and two up, three up, and actual color pass here, which is the last one because yeah, this is actually called the post GLSL, and it's also doing it's also accepting the glow. You can see the glow color here is accepted and it's doing some operation here. So we have 4 steps down and 4 steps up. And this is important to know because we may think that this is the glow, but the glow is actually 4 steps down. So this is first step down, this is second, third, and fourth. And fourth step up. So this is first step up, second step up, third step up, and fourth step up. So now you can understand why I tell you that this is important to count the step. This is actually the post-processing. So if you measure this thing with the control and click, so this is the where glow is starting and this is where the post-processing is ending. Yeah, this is, you are thinking, this is 13 milliseconds. Okay, so feature Wojtek here, and to clarify a few things, because I noticed I actually overestimated it a bit. So what is actually happening here is that you actually see the groups of draw calls in the PVR tune, which means this last step, this here, isn't actually a full like post processing, and it is a post processing GLSL file and the UI draw call. So actual glow and post processing is starting here and ending somewhere between here, which we saw is still freaking expensive. And it may be around here where we don't use any vertex still. So let's say it's, from what I remember, above 4 milliseconds. It may be around 6 milliseconds, but definitely not 13. Still, 6 milliseconds and post processing is crazy high. So yeah, that's short update. So let's say if we wanna have glow in our mobile application, we're gonna have to do something about this. And we saw in the Arduino debugger that those operations are very texture heavy. So what can you do to optimize it is basically do the glow only in the half resolution. So if you think about it, like if you read the article, the glow operation is kind of complex. On the downsample, we are, okay, I can actually show in code, but on the downsample, we actually are gonna take like 5 texture loads samples, and in the filter as well, because this is like a multi-view thing, which are we are not interested in. And on the upscale, I think we should take actually 8 steps on the upscale, 8 texture loads, texture samples. So doing in the full resolution on a mobile device, it's kind of wasteful, at least in my opinion. I mean, the result will be a bit more blocky if we don't do that, but it's obviously too much. And yes, so this is what we're gonna try to optimize for. Um, and yes, one important thing to note is that, well, not one, but we should be aware that the last pass is actually a different shader. So the three first passes in the Godot are in this one file, but the last pass, this one, is actually a different source code. So I would recommend like checking every time you edit something what kind of things are in this shader, and you will notice this one. This one is totally different. Like the other ones are defined best, but this last one has this get glow color, and this is actually the most expensive call in our full stack, and it's not in the same file in the Godot source code. So you're gonna be aware about that. But what we're gonna do? So basically, this is actually saving us a hassle because the first step is actually a filter step, and the last step is actually in this separate file called get glow. And my idea is to avoid doing glow on the first and the last sample. So basically, we're doing glow in the half resolution. In the first step, we just sample the original texture using linear interpolation, which is by default, in shader, in texture sampler, and we're gonna do the same in the last step of the upscaler, which should save us a lot. And I will gonna show you the final code that I got in a minute. And I decided to show you the changes to the glow actually in the Godot source code because, well, why not? So this is the full shader, and as you can see, Godot likes to combine vertex with the fragment, but because this glow is very simple, you can see that it's basically it. And what I did is I added I should say I removed the color samples in the filter step. So I just sample from the UV in the center of the current pixel, but because we are actually half of the resolution of the picture that we are or texture that we are sampling, it's basically using a linear interpolation. And I use the LOD one, but I think there are no LODs actually available, so it doesn't really give us any benefits, maybe even hurting us. So maybe I should change it to LOD 0 again. But anyway, and what I did is also I added offset and set it to 1.5, which basically means that I can sample a lot less and get a wider range at the cost of the precision of the glow. So I don't really care about the precision of the glow, and basically I am taking the samples further away, so I'm covering a wider area a bit instead of a half pixel, like 75% of the pixel away. And yes, so I am doing this in the down sample and up sample, and as you can see I didn't really change a lot in the up sample, um, except I actually did combine or separate the color wrapping into two separate variables. And you may think this is looking weird, and it kinda is, but from what I saw, it's basically giving me a better register usage. By separating those two calls, it's not stalling so much on all texture reads because they are added to the same variable. It's doing it in a more, complex way, but in two separate registers, which basically equals in better shader utilization, more shaders running in parallel, and overall improvement like that. This is, of course, not gonna work for every project, but it's working for me. And you can see that I don't have the app sample last step here because this is actually here in the post shader. And yeah, the post shader is actually only doing the same. So I'm not sampling all those 8 textures. I mean, all this texture 8 times, which should in theory be using cache or whatever, but the mobile GPUs are really bad at that. So it's using one texture sample here, and because of that, I don't need to divide by 12. But that's it. That's basically it. And about other modifications to the shaders, I have this one, which is basically again only linear to sRGB, sRGB to linear. This is included in the glow, so I had to do this one. And the copy shader. The copy shader is the last shader in our pipeline, which is basically copying our render target to our screen. So it's something that we have to do. And again, this is linear to RGB, which is expensive. This is not correct, of course, but it's fast. And it's a good approximation of the gamma 2 instead of 2.2 or something like that. And the last thing I want to, speak about, I mean, this is tone map, which is basically the same again, linear optimization, and thin GLCL, which is basically our main shader optimization. So this is doing what we did in the beginning. It's just moving this modification to this simple generative shader and kind of putting it inside the original Godot shader. And it's kind of complex as usual. It's really pain to work with this one. So I recommend doing all the optimization, the small, shaders that we get from the RenderDoc. And when you are happy with the results of the offline compilers, I remove the fog, for example, because I don't use it in my project. And well, it could take some work from the shader. So what I was saying is like one issue you can have during the development of the shader for the Godot is basically how to find the if-def preprocessor instructions, because they are always or sometimes very nested. So what I did, I just asked the ChatGPT or Gemini, hey, write me a script that will, find me everything that I need to know. And for example, I have this line of code and I want to know, I copied it before from the shader, and I want to know what kind of if-defs the shader is, this line is using. So whenever I move it around, I still have the same if-defs. And it just basically shows me the hierarchy of the if-defs. So whenever I move it, I need to, keep it the same and or recreate it or whatever, so it doesn't crash, or fix all the variants and things like that, which is making it very useful. And that's basically it. So whenever you do this, you can try to compile Godot, use your custom export template with all the changes we made, and we can try to see the results. Okay, so I just want to mention 2 other changes that I made. So in the C++ side, which is I changed the samples number for the glow to be 3 instead of 4 and make it a const, but doesn't really matter, which really doesn't impact that much, but yeah, every second, millisecond, microsecond counts, and I changed the precision to medium P, and this is done on your own responsibility. I'm not sure if it's a good idea or not, but yeah, it's the performance what matters to me the most, and like if I have some reports of issues, I'm gonna change it. And let's see, well, what kind of performance impacts do we expect? I also did other smaller changes, like in the environment. I changed the background to custom color instead of the gradient which we had before, to save like another millisecond or something like that. It was a full call which was making our GPU filling the full screen, which was very expensive. So I skipped it, and yes. So if I launch the game now on Android, mm, well, let's see. We have a monitor, and you can see we are at 80 FPS, 89. So it's 90 FPS. So the place where we started and the place where we are right now, it's giving us a lot to think about how optimizing for specific game the engine itself can give you performance increase. And let's see, like we can take a look at other yeah other uh, tools like RenderDoc and see how the drawcalls are different right now. So if we're gonna, yeah, okay, so we lost the connection. So let me actually reconnect it so you can see. So let me pause. All right, and here we are again in the RenderDoc, and we are loading the custom export version of new app, and you can see the color passes, the depth passes, everything that is looking right now here. It's kind of looking similar, a lot of less, less drawcalls here because we are not doing this, and we also have like different color mapper and stuff. But yeah, the game is kind of similar to what we started with. We remove some shadows, we remove some like non-important things. We can add them later with the settings or things like that for more performant devices, but what matters right now is the performance we get from the game itself on the mobile device, on the low end, because yeah, we want the game to run everywhere quite nicely. And one last thing I think that is worth noting or worth seeing is how does it look actually in the uh, well in the localhost environment. So let me actually run the game uh, manually so I can open it currently on device. I think this is this one. Let me see. Sorry for the yeah. This is this one, and let's continue because I have both versions, the original and custom export one. And yeah, so this is the current draw call or the current like view. Like you can see other like interesting things like how the pixel shader load is looking and register overload. It's still pretty high, I would say, in some aspects. Like here is 89, but like overall, it's looking a lot lower. And what is most important is, of course, not really those numbers, but the frame time, which is 11 milliseconds. And this is the number that is actually matter to you. And like If we want to take a look how well we did with our, for example, our glow shader, we can, let's disable this one. And let's see, we have now 3 steps down because we changed that. So we have 1, 2, 3, and 1, 2, and 3. So how long our post-processing stack? This is probably not the post-processing fully, but a bit more. I think this is also with UI, but I may be wrong. But this section now, which was taking before around, I don't know, 13 milliseconds, is now down to 4, which tells a lot about the improvement that we did. And yeah, this is the result of our work. So now I think this is the place where I will end this video. And of course, you can do a lot more to optimize it further. You can, take a look at the drawcalls, for example, and there's a lot of this disconnected again, but there's a lot of things that doesn't make the best performance, like whenever we do, for example, a color pass and we do the drawcalls, you can see a lot of the same instructions. So okay, we actually can do the action one, action this one, and like we have a draw calls. Yeah, like let's see. So this is our bush that we decided to take a look again, and we have like events for this particular draw call. And you see all those events, and like for example, the next one, which is also a bush. Yeah, I mean, there are some kind of events that shouldn't be really there. Like I can see like this 0 1 is doubled, and I can see like bind to texture 551, which is also here, I believe here. So this could be optimized, so we could minimize the draw calls number. And yeah, we could also try to squeeze out a bit more in the register count and things like that, but I will probably stop right here and well focus on different things and then optimizing the renderer, because I am quite happy for the type of the game that I'm having. So as a reminder, this is looking at 90 FPS with the, and yeah, it's kind of dropping whenever we use all those tooling, but it's still quite nice. It may be also overheating a bit, and but it's still way above what we had before. So it was almost 90 FPS, if we remember correctly. And we have all those post processing stuff still here. So we have adjustment, we have glow. We could enable the reflected lights again in our shader if we really want to, but I'm not sure if I really want to, so I will probably don't won't do that because I don't need that. And yes, our game can still look visually very similar to what we had before, but it's just performing differently. Yeah, so that's all. Thank you for watching, and I hope this helped you at least a bit and give you idea how, well, let's say complex can be optimization per game. Even though we are using the same game engine, you can squeeze a lot more if you think about like what kind of limitation your specific mobile game have and what kind of like trade-offs you can work with and what can you sacrifice and what you need to have enabled, and things like that can make a big difference in the mobile world.